Let's talk about second order transfer functions, second order filters. We've talked a little bit previously about functions that had an h of s that looked like a constant in the numerator, call it h0, and a denominator that was in our sort of standard form that we like, s over omega naught squared plus 1 over q times s over omega naught plus 1. I think we've talked about this before. We can evaluate this doing a simple Bode plot evaluation. At sufficiently low frequencies where s equals j omega and omega is real small, this thing will just evaluate at to h0. So h0 is the DC gain. All right? And at very high frequencies, then s equals j omega is very large. This term is much bigger in magnitude than this term, which is much bigger than this term. So this term dominates. So at sufficiently high frequencies, as omega goes to infinity, the gain becomes inversely proportional to it. The gain goes as h0 times omega naught over s quantity squared. So this says that our Bode plot associated with this guy looks like h0 at low frequencies. It looks like minus 40 dB per decade, that's frequency squared, at high frequencies. And what we've said before is that what happens in between depends on Q. If the Q is small, then we said this thing was something that was approximately Q times some omega naught. Well, we have omega naught. And this would be h0, this is, the frequency is omega naught over Q, where Q is real small. So this is okay, but if we use this in a filter context, this is not as selective as what we could get with a higher Q. So for a lot of filters, Q is a little bit higher. These guys will move closer together, and this whole thing will go up a little bit. We said that if we evaluate this transfer function for s equals j omega, so at s equals j omega naught, which is omega equals omega naught, then this term evaluates to j omega naught over omega naught quantity squared, which is just minus 1. That cancels this term. So at s equals j omega naught, the first and last terms cancel each other, and all that's left is the middle term at this particular frequency. So the gain at this frequency, this term in parentheses has a magnitude of 1, and we get a magnitude of q times h0. So at whatever value of q we have, the gain at this point is q times h0. So if q is real small, we'll have something at omega naught, which is q times h0. And if q is greater than 1, then we'll have peaking as we come out of here, again, with the value always q times h0. So that helps us get an idea of what these different plots look like. And plots with q not too far from 1 are frequently very useful in filters. And so we talked about that before. The main point I want to make now, again, though, is that this is a so-called low-pass transfer function, a low-pass, and it has this as its denominator. This is a second-order low-pass filter transfer function. So we can say this is a second-order low-pass filter, all right? And as we will see, for most applications, Q's somewhere in the order of 1 or maybe higher are, most popular. All right, so we can say things about that. Passes the low frequencies, attenuates the high frequencies pretty substantially, and then we have to kind of fit this complicated behavior in close to the transition frequency, and having a nice large slope in this transition region is what we talked about as being selectivity. Okay, so that's a low pass, and that's usually kind of where we start in a discussion of filters. Different kinds of filters, we're going to talk now, in addition to low pass, we're going to talk about high pass, band pass, and some others. The difference between high pass, band pass, low pass, and all the others has to do with the form of the numerator. So let's take this thing and change the numerator and do a high pass function. One way to do that, by the way, is sort of a nice theoretical thing, is do a transformation where I take my S over omega naught and replace it with omega naught over S. So if I take this transfer function and just plot it like that and do this swap, this is the low pass to high pass transformation. And it takes this thing in a log plot and just folds it over this thing and flops it around so that at high frequencies we're going to get a gain which we guess we'll call H infinity. Then it's going to have some kind of peaking, and then at low frequencies it's going to reach an asymptote which is plus 40 dB per decade. So before I even do the algebra, this is what a high pass is going to look like. And at the frequency omega equals omega naught, this will be Q times, which in this case I guess we'll call H infinity, which is the gain at high frequencies. So what does that do to the transfer function? I'll let you do it algebraically, but all I'm going to do, we're going to find that all of these things share the same denominator. Or we can build sort of families of filters that all have the same denominator. So in the bottom, in the numerator, I'm ultimately going to rearrange after I've done all of this stuff. I'll rearrange that. And when you finish all of that, you're going to get what might have been an H0. Let's just I'll call it H0, and we'll see what we want to call it in a minute. This is the corresponding transfer function for the high pass function that looks like this. So this is, I don't know, HP for high pass of S, something like that. Let's get this out of here. This was the low pass. And again, the transformation doing this would have just put some omega naught over S as I'll multiply top and bottom in my transformed thing and put S over omega naught. It flips over into the numerator. So to make a low pass transfer function, we have our denominator in whatever form. The numerator is a constant. To make a high pass, we have two zeros at S equals 0. So this is squared in the numerator. Now let's just look at this. In the limit of S being very small, obviously at low frequencies this thing approaches 0. All right? So that's how we get this asymptote. And when S equals real small, these two terms go away, and we just get gain that is proportional to frequency for low frequencies. For very high frequencies, this term dominates the other two. These two terms cancel, and we get a gain that is proportional to what I called H0. So maybe we should call this H infinity, because in fact, this is the gain we're going to get when the frequency is much greater than omega naught. And as usual, at S equals J omega naught, the value of this thing will be H infinity times Q. So if Q is maybe a little bit greater than 1, then we'll get a thing that has some peaking. And if Q was less than 1, we'd get a family of curves like this. So typically we'll be in this band somehow. Plus 40 dB per decade, all right? Flat at high frequencies. That's a high pass circuit, all right? And then we can, to do a filter design, as we'll see, you can choose the frequency that you want for this, choose the Q that you want, and the shape is then specified. Okay, so we did low pass, we did high pass. The other possibility, or there's a lot of possibilities as it turns out, all coming from changing the form of the numerator. If we want to make a bandpass transfer function, I can do it by putting in some H, and I guess I'll go back to 0, and we'll think about what it means in a minute. But this is now to the first power, so there's 1 0 at S equals 0, and the same denominator. This is going to turn out to be a bandpass transfer function, all right? And I'll just show you what it looks like, and then we'll make sure we believe it. Down at low frequencies, well, I guess we can do this algebraic. At low frequencies, where S is real small, this thing goes away, and the denominator is just equal to 1 for sufficiently low frequencies, but the numerator is now going proportional to frequency. So this is the slope of a single proportionality to frequency, so this is plus 20 dB per decade, all right? And at high frequencies, this term dominates the denominator. These things go away. This is to the first power. This one is to the second power. This thing is inversely proportional to S over omega naught. to the first power. So this is now minus 20 decibels per decade. So that's what this thing does at high frequencies. Of course, these two things will meet at a frequency which is S equals j omega naught. All right? So this is a bandpass. It's going to pass stuff in the middle. Now we have to evaluate as usual for the case where S equals j omega naught. In that case, this term becomes minus 1, right? S equals j omega over omega, j omega naught over omega naught is j squared. This thing turns into minus 1. It cancels this guy, and all we have left is this. So at that frequency, the S over omega naughts cancel, and we get a gain of whatever our H0 was times Q. So once again, the H0 times the Q that flips into the numerator gives us the gain at S equals omega naught. So this is like a standard resonance circuit. For increasing values of Q, this thing just gets narrower and narrower, and this thing just gets higher and higher. So it becomes more and more selective and passes one frequency and eliminates others. If you do this for very low values of Q, if I just redraw this, for low values of Q, you may see individual omega 1 and omega 2 things, where omega 1 is approximately omega naught times Q, where Q is much less than 1, and omega 2 is omega naught divided by Q. So I think we've seen this before. And on a log scale, this is just the middle of these. These are two like real poles separated like this. Again, this height would be H0 times Q, where in this case Q is relatively small. So these would just tuck underneath here in that case. It's not uncommon to have pretty high values of Q in some circuits, so we may have bandpass filters with Q that's substantially greater than 1. That definitely happens in some cases. Here's an interesting thing about filters, and I'm not going to derive this, but if we look at a bandpass filter that has a shape that looks like this, and we come through here and say, okay, this was Q H0, but whatever it was, this is the gain at omega naught. If we call that 0 dB compared to something, and come 3 dB down from that, so if this is 0 dB and we come 3 dB down from that, so if this is 1, this is 0.707 on a linear scale, and define two frequencies, omega 0.1 and omega 0.2, these are the frequencies at which the gain is 3 dB lower than this. It can be shown that the 3 dB bandwidth of this thing, I'll call it the bandwidth, but it's the difference between two frequencies at which the gain is 3 dB down, then you can go through all this algebra and you can show that for a second order bandpass filter that the ratio of the bandwidth, the center frequency omega 0 to the bandwidth is equal to Q. Now some people think that's the definition of Q, but it's not. I mean, Q can be used more generally, but this does happen for second order bandpass filters. So if you have a very high Q filter, this thing will push up and everything will come with it, but the bandwidth becomes relatively narrow for a high Q. So that gives you a little bit of sense of how these things interact with each other. So the numerator, so far we had low pass, the numerator is equal to a constant. And a high pass, we had the numerator equals H0 times S over omega naught squared, and for a bandpass, we had the numerator equals some constant H0 times S over omega naught to the first power. All right? Again, okay, so that's enough of that. Now, that's not all that you can do. There's other possibilities in the numerator. So let's look at some of them. One is a so-called notch. Let me show you something real quick. Or not. If I want to build a notch, it's going to look like this. At most frequencies, the gain is 1, and as we get close to omega naught, the frequency is going to drop out. And if I had done that right, just to do that, this is the frequency omega naught. This is some H0, and this is also going to be H0. And then the gain is going to be essentially go to 0 at some frequency. Well, we just have to figure out how to write a numerator polynomial such that the numerator will go to 0 at that frequency. And if you've been paying attention, you can probably guess how to do this. I'll let you think about it, but the answer is s over omega naught squared, leave out the middle term, plus 1. Again, when s equals j omega, this thing is omega naught over omega quantity squared, which is j squared, which is minus 1. This thing has 0 gain, minus infinity on a dB scale at a particular frequency. So that's good. If you wanted to eliminate a particular frequency, you could build this so-called notch filter. So let's go ahead and N-O-T-C-H. In this case, the form of the numerator is some constant onto s over omega naught squared plus 1. This thing has roots, numerator roots in the s-plane. Remember that our s-plane interpretation of this whole thing had real and imaginary parts, and our poles are always out in here. When we had, this is the roots of the denominator for real poles were on either side of a circle of radius omega naught. For filters, a lot of times we want q's greater than a half, and so we'll get complex conjugate poles that'll be on a circle of radius omega naught. Where are the roots of this guy? They are at plus and minus s equals j omega naught, right here. Minus j omega naught. At some point I'll show you a nice way you can use these pole zero plots to get a feel for what's going on in the circuits, but we'll put that aside for the moment. Okay, I got one or two more tricks I can do. Yeah, I got several more tricks. There's a lot of interesting other filters we can do. So something that's very similar to this is to put a notch at some frequency other than omega naught. Here's our pole zero plot with our complex conjugate poles, and then I'm going to put a notch at, say, plus j omega sub n. This is just values on the j omega axis, but at values other than omega sub n. Now I'll let you think through this, what this looks like, but here's what it does. At low frequencies, the s's all go away and we get h0. At very high frequencies, the 1 goes away, the middle term goes away, and everything is dominated by this term. And so we get a gain, which is again constant. The s terms cancel, but this thing is going to be h0 times omega 0 over omega sub n squared. So this is some kind of h infinity gain. And apparently it's got higher gain at low frequencies than it does here, so it's kind of a low pass sort of a thing. But what happens is, as we get close to s equals j omega naught, these two terms cancel, and this thing maybe undergoes some peaking depending on the value of q. And then at some frequency, this thing has to really go fast now because it's headed to minus infinity as it approaches omega naught. So somewhere out in here is the frequency omega naught, and out here is the frequency associated with the notch, omega sub n. So this is sometimes called a low pass plus notch function, LPN, and it's the same type of numerator that we had over here, except it's got s over omega sub n, where n is the notch frequency, and to make it a notch, the omega sub n has to be at a frequency which is, actually I drew it wrong before, omega sub n has to be greater than omega naught so that this thing will be lower than that. So I drew the pole zero locations. The j omega sub n is out here, and minus j omega sub n, where this is the ratio omega naught. So this is the low pass notch. The reason I was confused, if I take this same transfer function and simply assume that omega notch, that omega sub n is at a lower frequency, all the algebra stays the same, but the form of the plot changes and it becomes a so-called high pass notch. So if we do a high pass notch function, at low frequencies it is H0. At high frequencies it is at H0 times omega 0 over omega n quantity squared, but I'm going to now let omega sub n be less than omega naught so that this thing is higher than this. As we come down in frequency, we'll have potentially a little bit of peaking close to omega naught, and then this thing has to hurry and go down really fast, so this is very selective, very steep here, as it tries to find the frequency omega sub n. So this is a high pass notch, and that's the same expression except for we have a different relationship, in this case with the omega sub n at lower frequencies, so we come down. This is real handy if you wanted to have very selective filter and really steep slope right here, or if you wanted to do high pass filtering and really eliminate one frequency. Or you can just think of it as a very selective filter, but you're giving up the fact that at low frequencies you still have some gain through it. So there's some trade-offs there. All right, so that's most of the interesting things. There's other possible places you could put poles and zeros and make things that don't even have names with this. There's one other that is sort of surprising in this whole context. There's one other possibility, and that is to have, let me just give this a new name. I'm just going to call it, well, I'm going to put omega naught, and this may be surprising. This is an interesting one. I'm going to put a minus sign in here. This is like we have a negative value of Q, S over omega naught plus 1. This one is called an all pass. I'll say AP. And I don't want to write that whole thing down, but this is the same as the numerator is the same as the denominator. I guess I'll write it. But it's got S over omega 0 squared with a minus sign in here. And so what this thing is going to do, hope you can see that, what this thing is going to do is put poles and zeros in a strange set of places. Here's our circle of radius, so that's the circle of radius omega naught, and the poles are over here, and here's the deal with this one. The zeros are over in the right half plane to the same extent that the poles were in the left half plane. Now, why in the world would you do that, and what does this do? And what in the world could it be to be an all-pass filter? If you look at the magnitude of this thing, at high frequencies, the gain is dominated by the ratio of these two, and they dominate to 1. At low frequencies, it's 1. And even when you're at some other frequency, the magnitudes of these things, the intermediate terms, are equal to each other. So the fact is, this has a very boring magnitude plot. At all frequencies, independent of frequency, this thing has a gain that depends on, that is independent of frequency. So why would you ever do something like this? Well, the phase is a more complicated function. This thing then can be used to add phase shift to a system and adjust its phase. So strange applications for the all pass. Okay, so to summarize, and we'll come back later and talk more about choices of different denominator polynomials, but entire families of filters have the same denominator, and the types of filters, whether they're low pass, high pass, etc., are all done by choosing different forms for the numerator. And that's how these different kinds of filters are created.